Good morning, everybody. Let's talk about angr. Angr is a general-purpose binary analysis platform written in Python. It's meant to accomplish all sorts of tasks, be very flexible, and to basically allow you to have the tools that you need to perform whatever sort of analysis that you want to with sort of maximum intuitiveness. So, considering that I'm pretty sure most of us are CTF players, we've all seen that angr is a reasonable tool for solving crack me challenges. So if you've never used angr, that's the power of symbolic execution. Let's see, what do I have here today? I have an example of a fake backdoored firmware for us to examine. We sort of just look at this source code for a second. We can see that the authentication function to whatever this fake firmware image is, it has a bit of a backdoor. There's just a hard-coded strcomp for this so sneaky password that can be basically the idea is you run the program and you're asked to authenticate. Oh boy, this is not a very well written program. And basically, the backdoor is such that if you enter so sneaky as your password, you get access regardless of what your username is. This is obviously an interesting application for a lot of security things. If you can detect these things automatically in firmware, that's very nice, because we've seen again and again that especially wireless routers enjoy backdooring themselves for whatever reason. So what we can do with angr, so pop open a Python shell, is once we just load up our binary, then all of a sudden we've got this interface into the binary blob and the associated semantics. So if you're unfamiliar with symbolic execution, it's basically, I think it's traditionally considered a static analysis technique that sort of runs through an emulated version of the program using symbolic variables instead of concrete ones in order to perform computations and comparisons. And whenever you see that a program would branch, but the branch condition is instead of a value, it's a set of symbols, well, you can just take both branches. So let's set ourselves up with a path group to explore this program. A path group is a set of paths. If so we can look at the set of active paths, and we can see that the only path active right now is at the entry state of the program, at the entry point of the program. And if we step the path group, we can see that the set of active paths has ticked forward a little. And so if we just continue stepping, so if we just sort of continue stepping, we eventually see that, this could take a second. There, we've suddenly ended up with two paths. Well, what happened? So if you look at, if we look at the source code of this program, you can see that, well here, let's do this first. Let's open up this in IDA and figure out what address we just branched on. Okay, so when we say we've got a path here and a path here, the first path is now at this address, and the second path is now at this address. So, well, it's clearly we've just gone through this branch statement, and we've just suddenly decided to take both branches. Well, the fun thing is that each each emulated program state keeps track of the constraints, as we call them, that are placed on the path by following given branches. So the fact that this path went this direction is now ingrained in this path object. So we can now perform constraint solves. With a constraint solver, we use Z3 in order to figure out what elements in this state must be based on the fact that the path has gone down this particular route. So you can see that there are 3 paths through this function, and ultimately 3 paths through this program entirely. So if we just, so let me kill this. So we can just run the path group until all of its active paths finish. Second, cool. So now we have 3 dead-ended paths. Like I said, there are 3 paths to the program. And for each of these paths, we can then access the actual emulated state, and then we can from there access, this is a bit of a hack, but you can access the output of the program through post6.dumps1. So this will print out one possible concretization of the output of the program. So this is one of the paths that authenticated me. So then if I look at another one, and then another one. So there's 3 paths. One of them is you fail to authenticate. One of them is you authenticate correctly. One of them is you authenticate with the back door. We can distinguish them by so this dumps1 function is sort of a helper for, it means print out a concretization of file descriptor 1. So if I want to print out the input, I can just print out 0. 1, 0, 1, 2. So you can see this is clearly the one that has used the back door in order to authenticate. You can see that there's just this concrete, meaningful string sitting in the output, and then the other 2 are just sort of random data that Z3 said, oh, it could be this, whatever. So there's symbolic execution. You have paths and that are constrained and then you can use a constraint solver in order to pull out correct values for those. So this is obviously applicable for doing crackmes, for finding backdoored firmwares, etc. So then, I don't know how much time I have. If you want to do something a little bit more complicated, like find vulnerabilities in programs, there's an example I've presented before about finding the high-profile bug from last winter in Grub, where if you press backspace 28 times and then return, you get a rescue shell, which is a lot of fun. This crypto.mod is a copy of the actual vulnerable image. Since the last time I gave this presentation, I've actually upgraded my laptop, and now I no longer have this installed. But this bug file, this bug.py file, is an actual script in order to find the program. It's 70 lines long, and it would probably be condensed since this was written a year ago, and since then we've updated our interfaces pretty substantially. And pretty much all of this from here up to here is pretty much just setup. Just enabling us to even analyze the grub environment, which is a pretty interesting thing about angr. It lets you instrument and tweak your analysis environment in pretty much any way you want. We do give you pretty much full control over the analyzed binary space from a supervisor perspective. So it's just setting up all of the library functions that the module would normally have to import, but we don't really have those available, so we just got to do it. And then down here is the actual analysis. So what I'm going to first do is I'm going to switch to a naive version of this analysis. So the idea is so for those of you unfamiliar with the bug, the idea is that there's this loop that if you there's the input loop, and if you can go through the input loop such that you've pressed backspace 28 times and then exit the loop, then that's the crash condition. But so this is a demonstration of what happens when you just try to symbolically execute through that loop. So it's finding lots and lots of paths some of which are dead-ending, none of which are crashing. And you can see it's just sort of slowly slowing down as it sort of gains more and more paths. And if you sort of look at my memory usage, you can see it's going to start. Interesting, we've improved memory usage quite a bit since last time. So regardless, it is slowing down pretty badly, and if I did let it go, it would eventually out of memory me. But I like this laptop, so let's not. But so that was just a naive symbolic execution to see if I can find a bug. I'm defining a bug in this case as a path that jumps to the address 0. You could pick a better metric for that. But then in order to actually do this correctly, you just have to add your own little instrumentation in order to check the uniqueness of a path. That's what I've done here. And the idea is, of course, that symbolic execution is a very dumb tool, and in order to do really smart things with it, you need to sort of inject your own human intelligence a little bit. So this was based on my initial attempt at solving the problem was what you just saw that there was a nasty state explosion. I was able to debug this very easily using angr and discover that, well, there's a lot of wasted effort being put in on the behalf of the program. There's a lot of entering characters and then deleting them and then entering more characters, pressing the home button multiple times in a row. That's not actually interesting and not actually gaining us any new useful stuff in the search space that we're searching. So if we just add this very, very simple predicate that says, well, at every point, the program's registers must be unique, otherwise we don't care about this, we've already seen it. It's very easy to write, it's 20 lines, it could be condensed a little more even. Then we just enable that, and all of a sudden the analysis load is much more reasonable to be processed by angr, and in almost no time at all we find our way through the loop and find the correct crashing input, which is 28 backspaces and a return. So we used angr in order to play in the Cyber Grand Challenge this last August. I'm from Team Shellfish, obviously. We successfully hacked our way into the final round of the Cyber Grand Challenge and then successfully hacked our way into the top 3. So we're pretty proud of that. And angr underlied pretty much that entire effort. We used much more very advanced techniques similar to this on some level in order to actually find and exploit bugs in a totally autonomous setting. I'm assuming you all know what the Cyber Grand Challenge is if you haven't been living under a rock for the last 2 years. If not, But so that's very nice. That's a very simple application. But what if you actually want to do more complicated static analyses with angr? Well, that's another tool that you can do. It's another thing that we let you do. So I've written here a very basic demonstration of what's considered the most basic static analysis available to that a program might want to be able to do, which is as a signedness analysis. So you want to be able to say, at this given point in the program, could this value be positive? Could it be negative? Could it be 0? And I put together something to demonstrate that you can do that pretty easily with angr using the tools that we give you. Here, let me demonstrate this really quick. In angr, there's a concept of an analysis, which is just a bundled set of analysis logic. So if I import angr again, angr.project of this binary. Just under p.analyses, you've got a whole bunch of built-in analyses that we've written for projects with the lab. I work in the Sec Lab at UCSB, University of California, Santa Barbara. And in order to support our research, we use angr, and we use all these different analyses that we've written for angr. The most common one is, of course, a control flow graph analysis. Or there's data dependency graphs, there's loop finders, there's static binary rewriting in the form of the reassembler, et cetera, et cetera. You can just, but the analysis interface's angr is highly pluggable. I didn't want to do that, I wanted to say it here. You can just write your own analysis and then register it. Here I've written this very short analysis, the sign analysis. This is the entire length of the analysis body. There's a little bit more in terms of just set logic and sign logic. But ultimately, if I go in here and then first import angr, then import sign analysis. Oh, lordy, hang on. Should have tested this first. There. Give me a second. Definitely should have tested this first. There we go. So now, if we load up this project again, you can see that we've been given analyses sign analysis. So if we just say the sign analysis result is here, give it a second. Here, let's take a look at what this program actually is. Sign analysis allcomps.c. Basically, this program is just something that tests all the possible different kinds of comparisons with two sets of concrete values. So sign analysis, I have set it up to give us a result, which is a mapping from basic block address to sort of the state of how everything is signed. So like, for example, if we just say results.values, it gives us all actual states, and then if we say like x.regs for x in here, we just see all the possible different register states. So here we saw like, there's a lot of different places. There's the value that things could be concretely 0, concretely positive, or it could be any of positive, negative, 0. And this is just based on a very simple static analysis I wrote in order to do that. And it works based on this sort of general framework for analysis we've provided to you called forward analysis, which sort of enables you to provide a minimal set of analysis information and automatically just sort of pushes you through just the binary analyzing the control flow graph for whatever properties you like. And it's based on, so this file looks pretty big, but all it is just information on how to like perform union and intersection of these sign sets, and how to represent a sign. Other than that, it's not a whole lot of stuff. I wrote this on the plane over to New York. It's just a very simple thing that you can do in order to say, well, let's say I start with, here, let's talk about this pre-analysis. So we start we start with just the entry point of the program, and then at each step we extract the information about the signedness properties of the state, and then log it, and note that if we have not gained any new information, we stop. Otherwise, we do perform a symbolic execution tick of the state, and then we just keep propagating until we run out of new information to find. So that's pretty simple, and it does in fact give you some meaningful results over here. So the angr system is something that I've been developing on for the last year or two. It's very well documented. We've got documentation both in the form of a book and also in the form of an API reference. And we're pretty good about support. We've got an IRC channel, we've got a mailing list, we've got lots of places to open issues on GitHub. Basically, if you need help using angr, I will probably help you personally. That's usually the way these things work. That's pretty much all there is. I would be happy to take your questions.
Okay, got a question over here.
Do you find it hard to trade off between the support role and actually developing for angr? Like trading off time-wise?
Yes.
Could you elaborate a little bit on that?
I mean, in addition to doing support work and also research and binary analysis, I also, through part of my efforts in the CGC, I ended up becoming embroiled in the Python packaging of several libraries. I'm now in charge of the Python distributions of Z3, Capstone, and the Unicorn engine, which is a lot more time than I would have liked to be spending on distribution and learning how to compile things 4 different ways on Windows. It's fun, though. I enjoy it.
Okay, well, while we're waiting for other people to think of, we got one down here.
Hey, so I've been pretty impressed with the documentation for angr, and I'm just wondering if you have any thoughts on how you either, got yourself, motivated yourself to write documentation, found time to write documentation, thought about how to write good documentation.
So let's take a look at the git blame stats on the documentation repo. We have a script to blame automatically and get stats. Blame.sh angr doc. Bash blame.sh angr doc. Yeah, I have the most lines in the documentation repo. It's me. I don't know. But basically, what helped a lot was setting up a testing infrastructure to make sure that to actually verify that all the code we stuck in the documentation was correct and imported and ran. And when I did that, we found that, wait, we've got a lot of stuff that's broken. And it was a pretty simple task to go through and fix things. And every time I fixed something, I was like, well, I could just continue writing something here. Or generally, I do a lot of, generally it's my job in the angr project to work on the global design of the project. So usually my refactoring projects start with, well, there's this problem that the interface isn't convenient enough here and doesn't represent an actual hierarchy somewhere in concepts of binary analysis. Then I go design a new thing, implement it, and then document it. So it's making sure that these things are usable is very much a large part of my role in the project. So. Anyone else?
Okay. Yeah, so actually I have a question, which is, so are there any sort of analyses that you wish were in angr, maybe that are really cool and were published in some paper recently that haven't been implemented yet that maybe someone here could go and implement? Do you have a top 10 analyses that you would like?
So let's see. In terms of cool, interesting static analyses, an implementation of any of the type inference algorithms that have been published in the last N years, those would be very cool. I tried implementing those. I'm way too pretty to do any sort of real math. So, so most of my type inference work is limited to various limited pointer analysis, but some real lattice-based or push-down automata-based type inference would be really, really cool. Some sort of points-to analysis would be really incredibly helpful for now analysis of C++ programs. We kind of fall a little flat in that area right now. I think we already actually got affine relation analysis down. The control flow graphs are pretty solid right now. That's about it. Right now, the project that I'm working on is rewriting the bottom level of angr, the actual emulation core, in order to support pluggable interfaces. So right now we support execution either symbolically through an emulation of the libx IR or concretely through Unicorn engine. So theoretically in the future you could plug in miasms, implement miasms symbolic or concrete emulation, or you could we could implement something that automatically takes your state, spawns a new process, dumps the memory into the new process, dumps an AFL fork server into the head of the process, and automatically begins fuzzing for new inputs just directly from the current state, from the current angr state. So that would be a lot of engineering work and probably not anything that we would really have time to do, but just different execution backends would also be an excellent point of contribution in the future.
All right, thanks. That was a great answer. Okay, do we have any other questions from the audience? Because I could keep asking questions all day and possibly will. Okay, we got one over here.
Can you comment on its support for ARM64?
ARM64, it's there. Angr, CD, binaries, CD tests, CD, AR64, file, star. Yeah, all these are ARM AR64 things. If we load up angr, if I load the right virtual env, here's the well, they have the test arrays program. So here's the project. It's got an arch of ARM64, and let's check if we can do if we can do concrete execution right now. Factory.path group. Please work. Please work. Please work. Zero.state. Come on. One dumps 0. So for basic stuff, it does work. That's the intended output of the program. The problem in supporting any architecture is the environment model support. So for example, I imported this, and our loader, which I wrote in the course of an 80-hour hell week, complained about an unknown elf relocation, which is normal. Because when we load this, it does try to dynamically link against any shared libraries that it can find. So we do have the libc and the LD for this architecture just lying around here. Generally, the sticking points for support of an architecture are syscall mappings and emulation, implementation of relocations, including thread local storage stuff, and sometimes on really exotic architectures, in order to support, libvex will lift some of its exotic instructions with very strange operations that we don't have supported, so those have to be implemented. Other than that, so those are the barriers in order to support some new architecture. For example, if you were to write a libvex lifter for MSP 430, for example, you would have to write lifter, the architecture definition, the loading support, so the relocations, and then provide a syscall mapping. And I think that gets you like 90% of the way done. So, hope that's satisfactory.
So speaking of libvex, I know that the Angr team has done sort of a lot of work, extending libvex's support for various instructions. So I guess could you say a little bit about, how do you guys then try to upstream those changes back into libvex, or?
I wish. Here's our fork of libvex at the moment. Git log. Last time we synchronized with upstream was July 2015.
Okay, so at this point, more of a fork.
On top of them are a couple of things our patches on top of that are just some basic bug fixes for analysis. I'm not really sure if they're bug fixes because really they help our analysis. We don't know if they help Valgrind. I should clarify for anyone who's not really familiar. So Valgrind, which is a very important tool, runs by dynamically translating code into this sort of intermediate language called Vex, which is conveniently very suitable for analysis. So we've taken the language core of Valgrind Vex and forked it and sort of made it a little more useful for analysis, which basically means messing with it so that you can compile it from multiple architectures at once, so it can be compiled from multiple architecture endiannesses at once, so that if it runs into a decoding error, it doesn't like abort your entire Python interpreter, things like that. So it's definitely something that I would want to upstream. And recently, I've gone through the process of upstreaming fork modifications to Unicorn Engine, to Capstone, to Z3. But Vex is going to be a lot of more of a hassle because they're a huge process. They're a huge thing. I guess it won't be too much harder than upstreaming changes to Queen, which I also did over the summer. Yeah, stuff like this. Yeah, so I'm pretty familiar with the 300,000 lines of C that are libvex, and I have the ability to modify them and not cause everything to fall apart. So we've been working on that. Our fork is automatically installed when you install angr.
Okay, cool. So I think that we're about out of time for questions, so let's just thank the speaker again.